The name of this unit is absolute value, functions, and equations. We'll start with the graph of an absolute value function. It starts at 0, 0 and goes up 1 over 1, up 1 over 1, up 1 over 1. But then on the left side, it also goes up 1, left 1, up 1, left 1, up 1, left 1. And we have this nice symmetry on an absolute value graph. And it works out because the absolute value of 3 is 3. And the absolute value of negative 3 is also 3. And so hence the symmetry. When we talk about domain and range, domain is x, range is y. If you look at that graph, the arrows are pointing forever and ever, sort of upward and out. So the domain is actually, when we think of the x-axis, this thing will cover the entire x-axis if it keeps going. So we say that the domain is all real numbers, abbreviated like a fancy R like that with 2 sticks. The range also is infinite because it goes up forever, but you'll notice that it never goes below 0 because absolute values are always positive. So the range for this one is going to be only y values that are greater than or equal to 0. Now we're going to get into transformations of that. This is called the parent function, absolute value of x. Now we're going to wind up shifting it and stretching it to make different looking v functions, but they're all going to be related to the absolute value graph. When you look at this is sort of complicated looking, but there's 3 numbers that I might throw into an absolute value graph. And the first one is the a value. If you ever see a different number out there, it's going to cause one of 2 things. A vertical reflection is possible. That happens if the a value is negative. Also, something that could happen if that a is anything other than a 1, it could vertically stretch or shrink our graph. Then we move on to the h value. The h value is either going to move things left or right. You can kind of see how it's attached to that x in there. So it's going to give x-axis changes. So the h is going to cause a shift of the graph. And sort of the same thing whenever something is added or subtracted, like this plus k at the end, that's going to have a shift effect. This one's not next to the x, so this is going to be an up or down, a y value type one. Now when you're graphing these practically, those shifts left, right, up, down are just going to move our vertex. Our vertex used to be at 0, 0 on the parent function, but if we move it left or right by h and up or down by k, that's going to move your 0, 0 to that point. And then that a value is actually going to just affect the slope of that v function. And I put the word slope in quotations because it's not a true slope like a line since it has those 2 branches. Let's just do some practice on that. So the first thing you should pick out is your h and your k because that's going to be your vertex. One thing to notice is that since in the formula it goes x minus h, this is always going to look like it's opposite of how it should be. If it says x minus 1, your vertex is at positive 1. Now the negative 5 shows up as it should because those y values are going to shift down by 5. Whenever I'm graphing that, I like to start at the vertex, 1, negative 5, and then again this a is going to be like our slope. So I'm going to go up 1 over 3, up 1 over 3. But then I need the mirror image of that, so I'm going to plot those points over there because every absolute value function will still look like a v. Now for transformations, you can count on the fact that every number is going to cause a transformation. We'll just go through them one by one. So the 1/3 is that a value. Did you notice that this graph looks sort of shorter, wider? That's because it got shrunken down vertically. We say that's a vertical shrink by a factor of 1/3. That's why that slope is making the v not as steep because it got shrunken down. And then for the 2 shifts, you just follow that vertex. And maybe it's even easier to look at the vertex we already wrote. That's going to do a shift that goes right 1 and another shift that goes down 5. As far as domain and range, this thing is still infinitely wide, so all real numbers for the domain Now that it's shifted down, it actually does go down a little lower than it used to, but it always stays above that -5. So that would be our range. Second example, kind of the same thing. We have to be able to pick out our vertex. It says x plus 3, so that's going to be a -3, +4 vertex. The a value is -2, so I'm going to go down 2, right 1, down 2, right 1. And then just mirror that out on the other side. And that's what our graph is going to look like. Now there's actually 4 transformations on this one. 1, 2, 3, 4. Even though I see only 3 numbers, this negative sign and this 2 stand for 2 different transformations. The negative, did you notice this was an upside down V? The negative is always going to cause it to reflect. So our first transformation is a vertical reflection. And that 2 made it steeper, so we call that a vertical stretch times 2. And then we have our shifts. Looking at the vertex is the easiest way for me to think about it. We shifted left 3 and up 4. Domain's going to stay all real numbers. It's still infinitely wide on the x. For range, this time it actually goes infinitely down. So our range is going to be all of the y values that are less than or equal to 4, since that's the highest it goes. Lesson 2 is just going backwards from what we just did. We should be writing our absolute value functions. I still think it's useful to write down what your vertex and slope are. So here I've got a vertex at 0, 6, and it looks like the slope is going down 3/1. It's my best estimation. So that means my a value is going to be -3. And then we're just going to plop it into this function. So they're asking us to write the function. A value is -3. The h is 0, so you could write x minus 0, or you could just leave it as x. And then that 6 goes on the outside since it's a y value. And that's all you have to do to write that equation. It might get a little trickier if I gave you a table. It might be just a good idea to throw those on a graph. So we've got a point at 0, 4, a point at 4, 1, and a point at 8, 4, if you can sort of picture that. So I'm thinking this looks like it must be my vertex. So we've got a vertex at 4, 1. We'd need to figure out what that slope is so we can throw an a value in there. And I didn't draw very well, but I believe this is going up 3/4 for its slope. Right, up 3/4 seems to work. So the slope on that one would be 3/4. And this one is just giving us the transformation. So do you know what shows up if you have a vertical reflection? And do you know what shows up if you're shifting down by 7? The vertical reflection just means there's a negative out front. You could put -1 if you wanted to, or just a negative. And we're shifting down 7, so that would be the number that's on the outside. So just going backwards from what we did in the previous lesson. Eventually we're going to solve equations and inequalities like this, but for now let's just do it the easy way. I've already graphed this absolute value function. It's got a vertex at -3, -4, and it's got a slope of 1. But what we're trying to do is figure out where that function equals -2. And that's like a y value of -2. So here's y equals -2. Where are those equal to each other? That would be right here and right here where they intersect. And since we're solving an equation that has an x value, we want to pick out the x values of those 2 intersection points. And we actually get 2 solutions to that equation, which often happens because of the shape of the v. You could try plugging those back into the equation. Both of those should work. We're going to talk about inequalities today too. So again, I have carefully graphed this part of that equation for inequality for you. And we are going to find out it's a 0, less than or equal to 0. And that would be just the part that's below 0, right? But it's this entire piece. And that entire piece happens to match up with lots of different x values, right? The way we're going to write that is that part of that v that's below 0 is all the x values that are less than or equal to 5, but bigger than 1. And so if it's just one region on the graph, I like you to write that solution as just one compound inequality, they call it. X is between 1 and 5. I've already got this piece graphed for you, and we're going to see where it's greater than 1. When we cut it off for greater than 1, that's actually two different branches, right? It's this branch right here and this branch right here. So we're actually going to have two separate parts to our answer. For over here, this part of the graph is anything smaller than -4. And this part of the graph over here is anything greater than 0. We aren't going to be able to combine those into a single answer because it's two separate chunks on the graph. So some of your answers are going to look like just an interval. Some of them will look like two separate pieces. In the last section, we solved these by graphing them and finding those points. Here we're going to start solving algebraically. That means we're going to be showing some work. So you know how absolute values, there's actually two numbers that have an absolute value of 10, positive 10 and negative 10, right? So I can sort of drop those absolute value bars because I know that that 3x plus 1 on the inside either has to equal 10, since the absolute value of 10 is 10, or that stuff on the inside has to equal -10, since the absolute value of -10 is also 10. Here's how we're going to get our two answers. Remember on the graph in the last lesson, these often had two solutions. So we're going to be seeing that again. Two solutions. You can count on that for pretty much every problem. The next example, you're going to want to get that absolute value stuff by itself. It's called isolating the absolute value. So I want to get rid of that 6 and that -4 before I do the split. So I subtract the 6, divide by -4, and now the absolute value is by itself. I know that there's two numbers that could have an absolute value of 6. Six or -6, and then we just solve both of those. And again, we got two solutions. This last one might be a little bit of a trick problem. Again, before we can do the split, we need to get rid of that 5 that's out front. If you're feeling really clever, you might be able to write down the answer right now. Can an absolute value ever equal -6? Absolute values always come out positive, right? The absolute value of 6 is 6. The absolute value of -6 is 6. There is no way that an absolute value can equal a negative number. And if you notice that right away, then you can say no solution. This lesson is a throwback to that time that we graphed to find solutions. I have this one graphed already. It said that this absolute value function is less than or equal to 0. And for me, I can see that that happens between 1 and 5 on the x-axis, right? But now our goal is to try to get that same solution only using our algebra rather than a graph. So on this first one, we're going to start by solving it just like we solved the equations last time. We're going to add the 6, divide by 3. Now all of these examples are going to be less than problems or less than problems. That's going to be important because our solutions are always going to be something like this, where x is between 1 and 5. There's always going to be sort of an interval that is our solution. So here's one way that we can do this algebraically. So we know that x minus 3 has to stay less than or equal to 2. And we know that the opposite of x minus 3 would have to stay less than or equal to 2. If we go ahead and divide that negative sign away right away, that tells me that x minus 3 has to be greater than or equal to negative 2. I divide it by a negative, so I have to flip the sign. Okay, now I'm going to just solve both of those. Here I'm going to add the 3. Here I'm going to add the 3. The word "and" in the middle tells me that I would want to join those up to make my final answer. So if x is less than or equal to negative 5 and greater than or equal to 1, can you think of what numbers those would be? Less than or equal to 5 and greater than or equal to 1. So I want those answers written in this form so I can see that x is between 1 and 5. Let's try another one. Got to get that absolute value by itself before we can start the split. X minus 5 less than 7, and it's less than, and then the opposite of x minus 5 less than 7, which if I divide that negative over right away, flips the sign. Solve both of those. Since this is an "and," I would like you to write it as a single inequality statement. The big number on the right, the small number on the left is the way I prefer. Those signs will always point the same way because that tells us that x is between negative 2 and 12. I have one more of those. On here, we would want to subtract the 7 first. And then divide this negative 1 away. Of course, if we divide by a negative 1, it's going to flip the sign. And at the time of the split, that's when you check the symbol. If it's a less than symbol, the word "and" is going to go between, and we know it's going to be like a single interval type of answer. When you divide that negative away, just remember to flip the sign. Since this is an "and," we'll have you write your answer in this form. Smaller number on this side, bigger number on this side, and you can always count on those symbols to point to the less than side. In this lesson, you do have to watch the symbol. So all of those last ones we did were less thans. This one's a greater. If you remember, when we did this by graphing, if we're talking about above the line, that actually gives us two separate chunks of the graph. This one was x less than negative 4 or x greater than 0, judging by the graph. Our goal is to get that without the graph to use our algebra skills. So sort of the same thing as those less thans, we're going to get rid of the half. And then it's time to split once that absolute value is by itself. X plus 2 greater than 2. This time it's a greater. If it says greater than, we're going to put an or in the middle. Or the opposite of x plus 2 is greater than 2. I always divide this negative out right away. When you divide a negative, it's going to flip the symbol. And then we just solve both of those. And this time it should be two distinct pieces, so we're going to leave them separate. Either the x could be bigger than or equal to, oh, I didn't need the equal. Either x can be greater than 0 or less than -4. There actually aren't any numbers that are both, so that's why you have to list those as two separate intervals. Just a couple more examples. Greater. And we always leave our greater than problems as two separate intervals with an or in the middle. Whenever you see a negative sign written with an absolute value, this one's probably solvable just by using your brain. Can absolute values ever be bigger than -12? Remembering that absolute values are always going to come out positive. Will positive numbers ever be greater than -12? And I would say all positive numbers are greater than -12. All of them. So in this case, the solution is all real numbers. You might have come to that conclusion doing the whole split thing, but I think that's probably the easiest way, is if you can recognize it. Again, whenever you have a negative number over here, you probably want to be thinking, oh, is this all real numbers or no solution? The absolute value symbol is defined as being the distance a number is from 0. So maybe it's not surprising that we can use that to stand for errors. The distance from a target is going to be your error. So let's just kind of draw this first one out so you can picture it. Mile marker 12. If you were 5 miles away from mile marker 12, you're either going to be this way by 5 miles or this way by 5 miles, right? So, I mean, we could do the math here. We'd be between mile markers 7 and 17. The point is not solving these, though. The point is setting them up as a model. So we are always going to say that x minus the target value, which is that number in the middle, equals how far away you are, or the error. So this is an equation with solutions of 7 and 17. But writing it like this tells us that the distance away from our target equals our error. This next one, Ethan is working at an ice cream store. He's supposed to get his cone filled with 8 ounces of ice cream, and it's acceptable to when you're within an ounce. You don't want to be way over or way under. So again, the target is 8 ounces. He's allowed to be a single ounce off. So that's going to be our 1 over here. Do we want his error to be smaller than 1 or greater than 1? So that word within means that we want to keep it within 1, so less than 1. Now, this is sort of up to interpretation, but he should be within an ounce. Do you think we would accept it if he filled it to 9 ounces? I mean, everybody's going to be happy with an extra ounce. Maybe we should think the other way. Would we be accepting this if he only filled it to 7 ounces? Would you say 7 ounces is within an ounce of 8? There is some interpretation here, but we're going to usually say that within means that we're allowed to be 1 ounce away, and that's okay. At a recent visit to the vet, Zelie was more than 3 pounds away from her ideal weight of 10 pounds. So the target was 10 pounds, and she was more than 3 pounds away. So most people would assume that means she's heavier. I think this picture is indicating an above by 3 pounds, but it says more than 3 pounds. So it could be that she's super skinny too. So more than 3 pounds away from her ideal weight. The distance from 10 pounds is more than 3. We can guess that the solution to that would be either she's weighing less than 7 or greater than 13. That would be the solution to that inequality. But really, I just want you to set up, for the most part, those models.